at infinity, there is a family of parallel lines that all intersect. At a point. At this point at infinity. And for example, you can take the point in the projective plane given by the line t1, 0, 0 in the direction of 1, 0, 0, and any line through this point at infinity will be given by a plane that is spanned. Any line that goes through this point at infinity in the projective plane will be given by the plane that is spanned by the vector 1, 0, 0. And some other vector, any other vector in fact. And so you get this picture that you get you get these planes, right? If you think about it, you have this 1, 0, 0, right? This is the line, and you fix planes that you fix an axis of a plane basically, and then you rotate this plane to obtain other planes and intersect them with z is equal to 1. And so you get this picture of parallel lines and planes like so. And so the parallel lines in the projective plane all meet at one point at infinity. And so we can infer the shape of the projective plane with this idea, right? It's roughly something like this. It's the normal plane with some sort of points at infinity, and for each point at infinity, there are parallel lines that meet at this point at infinity. This whole family of parallel lines that meet at this point at infinity. And another very interesting thing is that there's this one line at infinity that goes through all the points at infinity, given by the plane z is equal to 0. Now we move on to the conics in the projective space. I'm not going to draw much now because the illustrations are better and it's difficult to draw, so refer to the illustrations. We consider a parabola y is equal to x squared in the plane z is equal to 1. And we again want to consider all the lines, the set of all points given by the lines that go through this point, through the set of points y is equal to x squared. And so again we homogenize. And when we homogenize the parabola from y is equal to x squared, we get zy is equal to x squared. And so if we draw this in the plane and represent the green bit is the graph of this zy is equal to x squared, and the z is equal to 1 is the way to represent this parabola. And indeed it is a parabola, but it doesn't tell us about the topology, of the shape. But if we choose a different way to represent this, which we discussed earlier, namely the hemisphere, then we can obviously see that this is a closed curve. Which is homeomorphic to a circle. And so a different way to represent the projective plane gave us a seemingly entirely different shape, which with the help of which we could learn about the topology of this shape. And so the fact that representing the projective plane differently results in such different, sort of seemingly different shapes is suggestive of the fact that the projective plane is a much richer structure than the real plane. Now consider the hyperbola x squared minus y squared is equal to 1. We again homogenize to obtain x minus y squared is equal to z squared, and intersect it with the hemisphere. And so notice it's not a closed curve yet, right? Because we get two half circles. We get two half circles, this and this, But notice that earlier we said that we identify the points on the hemisphere that go through the same line. So in fact, they are half circles, but when we identify them, they become a circle. And once again, the topology of the hyperbola in the projective space is again a circle. Actually, exactly because it meets, exactly because it closes up at the point at infinity. Just another equation for a hyperbola, y is equal to 1 over x. Absolutely the same thing happens here. It forms half circles, and then we identify these half circles in a similar way. Let me just illustrate this quickly. That if you have this y is equal to 1 over x, then this will meet at the point of infinity here in the same direction, right? And so these will kind of be identified, and in a similar way these will kind of be identified. And so indeed it will form a closed curve in a topologically circle. But there's a much easier way to see this. Now these are the equations of the homogenized conics of the homogenized conics, a circle, a hyperbola, and another hyperbola, and we can actually show the topological equivalent by orthogonal changes of bases. Now this is if we have x squared minus y squared is equal to z squared, then we can rearrange and just relabel. Call this x star or x dash, y dash, and z dash, and this is going to be a linear transformation from z y. X, y, z is going to be a linear transformation, some matrix of x, y, z with a positive determinant and orthogonal matrix A, and so it's just a rotation. And so obviously they are homeomorphic to each other because it's just a rotation. And so if they're homeomorphic to each other as shapes in R3, then they are homeomorphic to each other as the curves in the projective plane that they were before homogenizing them. And similarly here, xy is equal to z squared. We say that let this be x dash plus y dash, let this be x dash minus y dash, and let z be z dash. We rearrange, and we get that x is equal to x dash minus, and we get that x dash is equal to x minus y over 2, y dash is equal to minus x plus y over 2, and z dash is equal to z. And this is again a linear transformation given by an orthogonal matrix with positive determinant. So again, it is a rotation. Let me just briefly illustrate. You know, if we start with something like this, you know, and then perform an orthogonal linear transformation, a rotation, right? If we had some curve like this, and then we move it to here, it's obviously a continuous transformation. So a homeomorphism, you know, the orthogonal matrix has an inverse, and so it's going to be continuous both ways and a homeomorphism. So they are topologically equivalent, and this is a much easier way to see this with the changes of coordinates rather than doing that whole thing with drawing them. And yeah, this is the book I used, and thanks to Keith and Elena for help with the presentation.
Okay, one very quick question. Can you quickly write back the very first thing you wrote, the definition of the equivalence relation?
Yeah, so x equivalent to y if and only if x is equal to ky for some real number k.
And if k is 0, what does that tell you? It tells you 0 is equivalent to everything.
If k is sorry, just give me a second. Now I'm just thinking if we could just exclude.
I'm thinking that would be a good idea too, yes.
Yeah.
And now which space cube quotient? Not our cubed, but